Hello, welcome back. Today, we want to learn about geometric sequences in series. So you may have seen a previous video, another video I did about arithmetic sequences in series. This one is about a different kind of sequences in series. So we'll explain what the geometric means and also how we create these sequences or series. So our goal is basically to generate these sequences to find what's called the common ratio. That's how we basically create a geometric sequence or series, and also find the value of a sum, whether finite or infinite. So a geometric sequence or series, so what this means is it says if you have a sequence or series in which each term after the first one is found multiplying the previous term by a non-zero constant, this is called a geometric series. So let's go over here to the right and just review. Remember what a sequence is. Looks like this. We have some numbers. We'll call them A1, A2, A3, and then we're going up to some number, AN. That's a sequence. So it's just some list of numbers, and there's usually some relationship between the numbers. Usually some way they generate, like A2 from A1, A3 from A2, and so forth. And then a series, essentially where we take these individual numbers, often called elements, the elements of a series, and add them together. So we do A1 plus A2 plus dot, 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 all the way up to AN. That's the difference in a series. A series, since we're just adding those numbers together. Now, if we have what's called a geometric sequence, basically it looks something like this. So once again, we have A1, A2, A3, and dot, 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 then AN, and then, of course, after AN, we have AN plus 1. So what we find out is essentially we can get from A2 to A1. So if A2 is some number we're going to call R times A1, and if A3 is also some number we call R times A2. So in other words, to get the second one, A2, we multiply A1 by something. To get A3, we multiply A2 by something, and then on down the line until finally to get A to the n plus 1, we multiply AN by the same number R. This is called a geometric sequence, okay? Where R is a constant, it's a constant value, and it's what's called the common ratio. Okay, and R can also be written this way. So AN plus 1 divided by AN. As you can see here on the left, so this common ratio written like this, and implies that once again, you get from any number AN in the sequence, you multiply it by this R to get the next element in the sequence, the next number in the sequence. Now, remember, an arithmetic series, basically these numbers are difference between one number and the next is just some constant. You add some constant, for example, to A2 to get A3. That's a arithmetic sequence. But here, multiply A2 by some number to get A3. That's a geometric sequence, as long as that number is constant. So let's look at some examples then with some actual numbers. So let's have this very basic sequence. So 2, 6, 18, and 54. Okay, and then it's continued. So this we'll find, if we take a look at this, now the first element is different, but let's find this A2. You notice that 6, of course, is 3 times 2. And then 18 is 3 times 6. And then 54 is 3 times 18. Then what we have then, so this is a geometric series with R equals 3. So that's 3 in this case is our common ratio. Okay. Now also these geometric series, they can increase or decrease. They don't have to get larger, they can get smaller. And also your R could also be a negative number. So they could alternate signs, for example. So they're many forms a series can take. This is a good example of a geometric series. Okay, so a few more things. So now that we know that R is 3, okay, so we know that that any number in the series, an plus 1 divided by an, is going to be equal to 3. And this also says that an plus 1 is equal to 3 times an. Okay, so we know that to get from one number to the next one, we just multiply the previous number by 3. Okay, now, next thing we thought look at is we have the, as it says here, the nth term of a geometric sequence. Okay, so the nth term of geometric sequence is given by this formula. So an is equal to a1 times r to the n minus 1. Okay, so we can find any term we want. So for example, just to verify this one right here, let's say in this series we have, let's write down again. So 2, 6, 18, 54, and so forth. Then here, of course, our a1 is 2, and our r is 3. So for example, I can actually verify. So my fourth term should be 54 if I do a4. So I'm having a hard time writing numbers today. If I do a4, then according to this, that's going to be 2 times 3 to the 4 minus 1. And that should be 2 times 3 cubed. Okay, 3 cubed is 27, so 2 times 27 is 54. Okay, check. So that's correct. All right, now let's do something else like a to the 10th. Okay, so you could also just complete the series, but this and find out. Just multiply 54 by 3 and the next thing by 3 and so forth. We're going to work and do it this way. So 2 times 3 to the 10 minus 1. Let's find out what that is. Okay, here we need to use our calculator. So 2 times 3 to the 9th, and once again, 3 to the 9th. That's not one most of us know right offhand, so let's take a look at the calculator. That's a large number. Okay, that's a pretty big number. That should be, according to this, 19,683. As you can see, this series gets large really quickly. Okay, so that gives us then, for this, we can find any term in this sequence by using this formula. Once we know the initial value, the a1, and also the common ratio. Okay, now let's actually look at another sequence. Let's do another example, then we'll also talk about one of our further topics. Let's do another example. So this one is practice this. So 1/2, 2/3. For some reason, I have a really hard time writing numbers today. 2/3, and I believe that's 8/9. Okay. Now let's work with this one. So here, now first up, if I simply give you this series sequence, doesn't imply it is geometric. We need to find that. But first, let's see what we know. So our first term, obviously, a1 is 1/2. Okay. Now, so let's take a minute and see. Let's try this. So if it is geometric, if we divide 2/3 by 1/2, we should get a number. Okay. Of course, we'll definitely get some number. So let's do that. So r is equal to 2/3 divided by 1/2. So once again, that's this rule right here. Now, if you remember, of course, dividing fractions multiplied by the reciprocal of what you're dividing by. So this is going to be 2/1, and that's going to be 4/3. Okay. Now, I'm calling that R. We don't technically know that's it yet, but let's also do the next one. Let's also make sure we get the same thing. If we divide 8/9 by 2/3, let's make sure we get the same number. Okay. So once again, we divide by, multiply by the reciprocal of what we're dividing by, 3/2. Okay. And so that's going to be 8. That's going to be 24 over 18. And okay, I want to make sure I wrote these numbers down right. That's going to be, yeah, that's also 4/3. Good. Okay. So our common ratio is then 4/3. Okay. So from this, we can find any number. Let's say we want to find the fifth. Okay. The fifth number in the sequence. So we only have the first 3. Okay. So let's do that. And so a to the 5th is going to be the original, the A1, the first element, which is 1/2, times 4/3 to the 5 minus 1. That's going to be 1/2 times 4/3 to the 4th. Okay, and if you remember how you multiply, if you have a fraction to a power, you can basically break that up. And so since you're going to have the numerator, so 4 to the 4th over 3 to the 4th. So raises both the numerator and denominator to that power. Okay, and let's continue it down here, running out of space. So the 1/2 out front. Okay, and then we have 4 to the 4th is a, what is that? 256. And then 3 to the 4th, I believe, is 81. So 81. Now, we can only reduce this a bit because obviously that is nothing common between 4 and 3. So with 2, we can actually divide this, make this a 1, divide this by 2. So 256 divided by 2 is 128. So this is going to be 128 over 81. So that's the fifth element, the fifth term of that sequence. Okay, so we can certainly use, so a good understanding, once again, to make sure, first off, make sure that it is, in fact, a geometric sequence. And we do that by at least testing a couple of the numbers, make sure we get, each time we divide a number by the previous number, one element by the previous element, we get the same ratio or the same number. And then we can use that then to find those other values. Okay, now, what we'll look at next is the sum of the terms. So this is actually where we get into really a series. So the one we do now then is we have like the sum of the first, say, 5 terms, first 10 terms, whatever, okay, of a geometric sequence. So this actually becomes a series that's given by this formula. Over here, now let's write it again. So we have S n, that sum is given by A1, and then times 1 minus R to the n over 1 minus R. And here, R can't be 1, because that would make our denominator 0. Okay, so let's actually use, instead of using this series, let's actually use another series. Okay, let's do an example of this. Let's do a different series. So let's do 3, 9, 27, and 81. Okay, and this is going to be in this series. You can go on for as long as you want. All right, so here, of course, our A1 is going to be 3. And if you check, divide 9 by 3 is 3, 27 by 9 is 3. So in this case, our R is 3. So this is a geometric series. Okay, so now let's find S5. So let's find one that's not very large. So the fifth, let's find, so basically S5, once again, let me write that better. Make sure my S's don't look like my 5s. Okay, so the fifth term of the sequence. So if we did this, 3, 9, 27, 5, and 81 times 3, and then multiply that by, added those all together, that would give us that. Okay, so S5, okay, according to this formula, is going to be A1, which is 3, times 1 minus 3 to the 5th over 1 minus 3. Okay, let's simplify that. And so that's going to be 3 times 1 minus, now 3 to the 5th is once again one you probably need to plug in your calculator. And that's actually 243 over 1 minus 3 is negative 2. Okay, you're getting closer. So it's going to be 3 times minus 242 over negative 2. And of course, this should be positive because all these are positive so far. We do this, so 3 times 242 divided by 2 should be 363. Okay, S to the 5th. Okay, and also let's do, so if we add one more term here, you can check this. So if you multiply 81 times 3, actually we get 243. So if you add 3, 9, 27, 81, and 243, you should get this number, which is 363. You can check that on your own. Okay. So that's how we can actually find the sum of what's called a finite series. So basically a series that comes to an end. We can also have infinite series, which we'll talk about in a moment. This is a finite series, so one that actually does come to an end. Okay. Now let's take a look at some other examples. And let's look at these in basically in series form. So let's take a look at this one. It's number 1, and we'll review what these symbols mean. So this large Greek letter sigma, but down here you have I equals 1 to 4, and that's going to be negative 2i. Okay. Now let's take a look at this. So here, now first off, we can actually write this out, and we can actually calculate this. Let's recall what everything means. So first off, anytime you see this big Greek letter sigma, that means you have what's called a sum. I mean, so whatever is here, you're gonna generate each number, and then you're gonna add them all together this many times. So what we're gonna do is, you notice we have an I right here. So our I, it's called the index, starts at 1. So first, when I is 1, we have negative 2 to the 1. That's going to be negative 2. Okay. Then plus, then I starts the next number, I equals 2. I equals 2, we have negative 2 squared. Okay. Plus, then I goes to 3, negative 2 cubed. Then I goes to 4, of course, is negative 2 to the 4th. And actually, we stop there because that's the top number. So this, the bottom number tells us where we begin. We go through that many numbers, adding them all together till we get to this number. Okay. Now, of course, you look at this. Of course, negative 2 to the first is negative 2. Negative 2 squared is positive 4. Negative 2 cubed is negative 8. And then negative 2 to the 4th is positive 16. Now, if we combine all those together, we're going to have negative 2 is 4 is negative 2 minus 8. Negative 8 is negative, I'm sorry. Negative 2 and positive 4 is positive 2. Minus 8 is negative 6 plus 16. Turns out this turns out to be 10. Okay, so it's a bit of a review in case you haven't seen it before of what these symbols mean. So once again, the big letter sigma means we're going to have a sum. We have whatever we're adding up here for each. This gives us each term, each element. Okay, we plug I into that, find that number, then add it. And when you start over, I equals 2. I equals the next number, plug that in, add that to the next one, and so forth until we get to the end. Okay, now we can also use the formula. To do this. Okay, so what we need to know then is, so basically, let's take a look at each one. So our A1, our first term, okay, and this sum is negative 2. So A1 is equal to negative 2. Now, what's our common ratio? Actually, this gives us our common ratio right here. Okay, we're raising to the I, essentially multiplying each one of these by -2. So here was -2. We started with that. This was -2 times -2, right? This was -2 times -2 times -2. This is what, or this number is what we got from the second term, which is +4 times -2 is -8. Then we took this number, -8 times -2 again, gives us +16. Okay, so our common ratio then is just this number here, -2. Okay, so let's plug that in. Let's make sure we get that. And so we have S4, the fourth term, is going to be A1, which is -2, times 1 minus, and here we're going to have -2 to the nth, which is 4. Then down here we have 1, just be careful with the signs as well. 1, now we're subtracting a -2, so down here it's 1 minus -2. Careful with the signs, and then just let's figure what this is then. Okay, so we have -2, 1 minus, now -2 to the fourth, we just did that up here. -2 to the fourth is 16. Okay, and down here it's going to be 1 plus 2. Okay, so we have -2 times -15, 1 minus 16, and down here we have 3. And so that's going to be equals +30 over 3, which of course is equal to 10. So equal to exactly what we expect it to be. Okay, so actually, so this is a much better way because, as you can imagine, if you wanted to do, I equals 1 to 100th, you wouldn't have to do it by hand, adding up creating all 100 terms, adding them up together. It's much easier to do this. That gives us for what's called a finite sum. Okay, as long as it comes to a definite end, we can always use this formula. Okay, let's take a look at another one real quickly. Show you one that's just a bit different. So number 2, let's say we have the sum k equals 3 to 9 of 3k. Okay, now you notice this one, this time our what's called our index is different. This time we're using a k instead of an I, but that doesn't matter. Once again, this means we're adding this up. So we're adding these terms up. So we start with k. This time we start at 3. Okay, which is a bit different. We're going to start at 3. And so we go to 3, plug in 3 for k, and add that to the next number. Then go back to 4. K becomes 4, and so forth. Becomes 3 to the fourth, and so forth, up we get to 9. Okay. Now, you may be wondering how we do this, because of course we can do it by hand and get all those numbers and add them up. But our formula here, okay, basically this says formula for the first n terms. So here, if we use the formula strictly, that would actually be just going from k equals 1 to 9. That wouldn't be 3 to 9. What we can do is, if you think about this, we're adding these up. This is actually the same as this. See if this makes sense. Oops, I forgot my term on the inside. Hang on. What we're going to do is we're going to subtract. We're going to break this up into 2 parts and subtract off what we need. So essentially, we have one part that goes from 3 to 9. So we're going to subtract here from 1 to 9 and subtract here. This is going to actually be 1 to 2. Okay, subtract the first term. So essentially this is this series right here, 1 to 9, with the first 2 terms missing. Okay, and so that's the way we can do this. All right, so let's do the same thing. So our first term, and basically these have the same first term, the same common ratio. So A1 in both cases is going to be 3 to 1, which is 3, and our common ratio is just going to be 3. Okay, let's do that. So this sum from k equals 3 to 9 of 3k is going to be, from our formula, this is going to be S9 minus S2. Okay, the sum of the first 9 terms minus the sum of the first 2 terms. So let's do those. So S9 is going to be A1, which is 3, times 1 minus 3 to the 9th. It's going to be a big number. Then 1 minus 3. Let's find that. maybe, yeah, we've already done that one actually. So the 3 times 1 minus 19,683 over minus 2. And so that's going to be 3 times negative 19,682 over negative 2. Of course, that would be positive. So let's do that. So times 3 is equal to, okay. So this one, what I get here is 29,523. Okay, so that's S9. That's first the sum of the first 9 terms. Okay, and S2 should be a little bit easier. So it's going to give me A1, which is 3, times 1 minus 3 to the n, or 3 squared, over 1 minus 3. And right, this would be much easier to calculate. This would be 3 to the 1 minus 9 over negative 2. That's going to be 3 times 8 over 2. So that's going to be 24 over 2, which is going to be 12. Okay. So finally, after saying all that, this sum of I equals 3 to the 9th of 3k, or sorry, k, it was k, not I, though it doesn't really matter, but let's be consistent. So k is equal to 29,523 minus 12, and that should be 29,511. And so that's the sum of those first 9 terms. You see, because these things get really large really quickly, it's a very large sum. Okay, now, last topic I want to take a look at today are infinite series. Okay, so this is talk about a finite series, one that comes to an end. What if we have an infinite series, one that goes on forever? Okay, so let's figure out how to determine that. And so sum of an infinite series. Okay, now an infinite series, just abbreviate that. Now, infinite series, of course, is any series that, or any sum that goes on forever. Any sequence goes on forever. You add up all the terms. Now, one of two things can basically happen. Either it can get really big, either in a positive or negative direction, essentially never settle down to a number, just keep growing, either positively or negatively, or it can actually settle down to a number. So it'd be hard to imagine that if you add up numbers, small numbers, you would finally actually come to an end. You know, it actually would just, in a number, but actually does, because what you're doing is you're just adding tiny amounts to each one. So let's take a look at an example of 2 series. So the one we've already done, we did 2, 6, 18, 54, ... This one, we'd say goes to infinity, okay? Or also say it was called diverges. If you take calculus, you may hear that term. Basically, diverges means keeps growing forever. And that's anything else that grows negatively forever is also diverges. Okay. Now, that's example 1 that diverges. Now, one that actually doesn't is something like this. So if we have 10, 1, 1/10, 100th, and so forth, 1,000th. This actually, what we say, so this actually equals a constant number, believe it or not. Because what's going to happen is essentially we're just adding tiny, tiny bits onto something. And so it eventually kind of settles down to a number, and we say this converges. We'll say this series converges, okay? So it settles down to a number, okay? Or actually, well, I'm sorry, I should say so the series, I should say, actually, I'm sorry, the sequence itself converges to 0, but the series, so I should back up, make sure this is clear. So you can say my sequence, the numbers are getting bigger, okay? And also the series, if I add them all up, goes to infinity here, okay? Now here, yeah, I should back up. make this more clear, more specific. Okay, here, this obviously goes to 0. As numbers are getting smaller and smaller, they're eventually going to be essentially indistinguishable from 0 as you get small enough. But the series, if I actually add all these up, the series actually equals some constant. Because essentially we're just adding tiny, tiny bits more to something, and so it never actually grows, kind of stays within a certain amount. Okay, let's take a look at a few examples of that. There's a formula for this. Okay, so the formula, as we see, so if repeat this for r, the absolute value of r less than 1, the infinite series converges to this number. So we say S infinity, okay, we have A1 over 1 minus R, okay, and it actually converges to that number, okay. But if the absolute value of R is greater than 1, okay, either goes, the infinite series goes to infinity or negative infinity. Okay, either goes to infinity or negative infinity. Never gets smaller. And once again, for some reason, I'm having trouble writing my numbers and letters today. Okay, let's look at a couple examples of this. Okay, let's look at this. So number 1. So we have the same notation for series. Okay, this one goes from I equals 1, and our term is going to be 5 times, in parentheses, 1/4 to the I minus 1. Now this one, we have an infinity symbol here. That means it goes to infinity. Okay, unlike the series we did before, this one, where it went from a number to 9 to a finite number, that's a finite series that stops. This one goes on forever. So we just keep creating these numbers, keep adding numbers to it. Okay. So on this one, we want to find, once again, our initial value or initial number, and then also our common ratio. So A1, so that's going to be when I equals 1. And so that's going to be 5 times 1/4 to the 1 minus 1. And of course, it's going to be 5 times 1/4 to the 0. Remember, any number of 0 is 1, so it's 5 times 1, which is 5. And our common ratio is just this number right here, 1/4. Okay, so if we do the infinite series, it says this is going to be A1, and our A1 is 5, divided by 1 minus R, which is 1/4. Okay, now, remember how to do this. Let's change 1. 1 is the same thing as 4/4 minus 1/4. And that's going to be 5 divided by 3/4. And once again, if you remember, dividing fractions multiplied by the reciprocal of what you're dividing by. It's the same as 5 times 4/3. And so, multiply fractions, multiply numerators, denominators together. This is going to be 20/3. Okay. So our S infinity, that's the sum. So actually what it means, even though we're constantly adding numbers to this series, but each number we add is smaller, and basically it ends up we're just simply adding up tiny, tiny bits to it that actually don't really make it grow. It makes it grow more within a bound. Okay, and this bound, what we'll get to eventually, is 20/3. Okay, and that's if you go on forever. If you stop somewhere, it's not actually going to reach this. It'll only reach this if you go on forever. Okay, then let's do one more. And sorry, just a minute, we find the one I wanted to do. Okay. So number 2. So the sum from I equals 1 to infinity of, I can only use K this time. It doesn't matter if it's something different. So you're familiar with different letters. about 7 to the negative k. Okay, so this one, what we do is actually need to work with we need to use a bit of a knowledge of negative exponents. Okay, so hopefully, if you haven't done negative exponents in a while, you remember that a negative exponent, what that means is, I can rewrite this, k equals 1 to infinity, as 1 over 7k. So basically, by negative exponent, you essentially take the term down to the denominator and get rid of the negative. Okay, now what I can also do is, since 1 to any power is 1, I can also write this, let's see, I think I'll do it below, as k equals 1 to infinity. This is the same. That's going to be 1 to the k over 7 to the k. Okay, I hope that makes sense, because 1 to the k is still 1. And then finally, I can, since I have both numerator and denominator the same power, I can finally write it like this. So k equals 1 to infinity of 1 over 7k. Okay, now, also one thing I should have mentioned in the last one. So here, our r we said is 1/4. I should have said here, and the absolute value of r is less than 1, which it is. 1/4 is less than 1. So this converges. Remember, if r was bigger than 1, then it's not going to converge. It's not going to settle down to a number. Although we can certainly plug it in the formula and get a value, that's not going to be correct. Okay, now, so now this is the same thing. All right, so now let's think about this again. So a1 is going to be when k is 1. Of course, that's just 1/7. It turns out our r is also just 1/7. Since we multiply each number in the series by 1/7 again. Okay, and of course, once again, this is 1/7. And we'll say the same thing again. And the absolute value of r, the absolute value of 1/7, is less than 1. So this converges. There is a sum. Okay. All right. So I can't seem to write numbers right today. So S infinity is going to be 1/7, which is a1, over 1 minus 1/7. Once again, I have to do little fractions. We have 1/7 up here. And down here, 1 is the same thing as 7 over 7 minus 1/7. Of course, that's going to be 1/7 divided by 6/7. And once again, to divide fractions, multiply by the reciprocal what you're dividing by. So it's going to be 1/7 times 7 over 6, where 7's cancel out. And what we're left with as our sum, as our infinite sum, is going to be just 1 over 6. Okay, so that means if we do this series, again, once again, if you go essentially to infinity, go forever, keep doing this forever, then you essentially will be identical to 1/6. Now, if you stop somewhere before, which of course in real life you would, doing it, even if you have a really fast computer doing it, but you're going to stop somewhere, it's not going to be quite 1/6. Be a bit less than that, but it'll actually be close to 1/6. Okay, because we're just constantly adding something to it, we're just adding tiny, tiny numbers to it. That eventually, it all things kind of settles down to this number of 1 over 6. Okay, so let's kind of review what we learned. So what we learned today are what a geometric sequence and series are. Basically, to get from one number to the next, multiply a current number by this what's called a common ratio r to get the next number in the sequence or the series. Okay, and we have a formula for the nth term of series. We can find any term we want, or if you knew the current term and the common ratio, you can always find the first term, for example, if you want to do that as well. Okay, well, then we have a formula to find the first n terms of a geometric sequence, add all these numbers together. And as long as it stops the first n terms, even if n is 1,000 or a million, this will give us the right number that comes to. And then finally, if you truly have an infinite sequence, it's possible for it to diverge, meaning it just gets larger. It either it's really big or either gets really big in a positive, negative direction, never settles down. R is bigger than 1. As long as our common ratio is less than 1, it will settle down to a number, and it will actually be the same as a number if you go forever with a series, then you actually get that number. Thank you. Have a good day.